Hi there, you're with Mr. Laurie, and this is our series of videos on integration. In this first video, we're going to be looking at approximating areas under a curve. But why are we doing this? Well, let's jump back a little bit and think about differentiation, which we've seen previously. Differentiation isn't just a bunch of rules to remember, rather it has its links to curves and the geometry of those curves. We know that when we take the first derivative, that gives us the gradient function. So if we have some curve, y equals fx, we can see that it has different gradients at different points, and each of those gradients at a different point can be represented by a tangent. The first derivative function gives us the value of the gradient of this tangent at different points. So we can see it's positive here, we've got a zero gradient along here, and so on. So there's this link between differentiation and the gradient of the tangent to a curve. Well, likewise, integration, which we're learning about, has its link to the geometry, except for integration, it's the area under a curve and in between that curve and the x-axis. So something like this. However, because of the unique nature of this curve, it's very difficult for us at first to know what this area would be exactly. So the best we can do to start with is to approximate this area, and that's what we'll look at today. So let's say we have the following curve and we want to find out this area. So if we're not quite ready to find the exact area here, what shape might be best to approximate this area? Well, the humble rectangle is a pretty good place to start. All we need to know to figure out the area of a rectangle is its base and its height. And we can multiply these two together. So how are we going to apply a rectangle to this shape here? Well, we've got two options. We can either do an inner rectangle, like so, which will leave out a little gap in here, so it will underestimate the area, or we could do what's called an outer rectangle, which will overestimate the area because it's going a bit above the curve. So we've got two ways of using rectangles, inner rectangles or outer rectangles. Now, neither of those were particularly great because we just used one single rectangle. But if we use more than one rectangle, we can get a more accurate approximation of our area. Let's start with the inner rectangles first, and we'll do 4 of them. Now, these 4 inner rectangles are going to be below the curve, okay, and remember they're going to underestimate our area. The first thing we want to do is actually break this length here into 4 segments. So we'll halve it, and then we'll halve those again, because we want each of our rectangles to have the same width. Alright, now the top left corner of each rectangle is going to touch the curve, and then from this point we'll go horizontally across. So there's our first rectangle, and then I'll continue this up for our second rectangle where its top left corner touches the curve. Go horizontally across, and we'll complete our 4 rectangles this way. Now, just the very nature of this particular example we're doing, this last one, it almost looks flat anyway. Okay, but there's going to be a little bit of error in there, and there's a bit more error here and here. Alternatively, we could do this using the outer rectangles. So let's have a look at what it would look like with outer rectangles. Now, our outer rectangles are going to be above the curve, and they're going to overestimate the area. This means that it's going to be the top right-hand corner of each rectangle that will touch the curve. So we might set this one up in reverse, in that we'll still break it up into 4. Okay, but this time it's from the top right that we're going across horizontally and then down. Okay, across horizontally and down. Pretty good approximation so far. But now's where we start getting a bit of an overestimation as the actual curve drops off. And there's our final rectangle. So we can see up here and here particularly where the rectangles go above the curve. Now, going from just one rectangle to 4 rectangles, as we've seen in these two diagrams, has given us a lot more accuracy. And this could continue. If we wanted to be more accurate, we could just go for more rectangles, 5, 6, 7, 8, 9, 100, right? And the more rectangles we have, the closer and closer our approximation will become to the exact value underneath this curve. And this idea of creating more and more rectangles, now they would become skinnier and skinnier as we got more and more of them, but this idea is really important. It's the essence behind integration, and we'll touch on that in future videos. But for now, let's do some examples to see how we can practice this approximation under a curve using rectangles. Find an approximation to the shaded area, and you can see the shaded area over here in the diagram. We've got the parabola y equals x plus 1 all squared, okay? And we can see the shaded area goes between x equals 0 and x equals 2, all the way up to the parabola, but underneath it. Now I've got two parts. We are going to find an approximation to this area first using 4 inner rectangles, and then in part B using 4 outer rectangles. So let's start with part A, where we're going to draw 4 inner rectangles. Might just zoom in a bit to give ourselves a bit more detail. Okay, so we can see that the width here is 2. So that means if we're going to have 4 equally spaced inner rectangles, they're all going to have a width of 1/2. So let's start to draw in our first rectangle. It's going to go to a half, and because it's inner, it's going to lie below the curve, and so the top left corner touches the curve here, and then we go across. Now we're going to have 1, 2, 3 more after that. So our second rectangle goes up at a half, touches the curve, then goes across. Drop that down. Now we're here at 1, right in the middle, so x equals 1. Okay. Now we know that this goes up and touches the curve at y equals 4. Go across a half. And then our final rectangle at x equals 1.5. Goes up, touches the curve, and there we have it, our final rectangle. So quite a bit short of the true area, but that's okay, that's what we expect, that the inner rectangles will underestimate the true area. So now to calculate the area of these 4 rectangles, we're just going to do it one rectangle at a time. So let's start with rectangle 1. We know its width is 1/2. In fact, they're all going to have a width of a half, but what about its height? I mean, graphically we can see that it's at 1, y equals 1, but how do we work that out just to be sure using the equation? Well, its height has come from x equals 0. So we can plug x equals 0 in to figure out the height. So f of 0 gives us 0 plus 1 all squared, and this is just 1 inside the brackets, and 1 squared is 1. So there we go, there's how we get our height equal to 1. And while that might seem really elementary for this first one, that'll come in handy for the other rectangles a little bit more so. So what is the area of rectangle 1? Well, it is simply its base, 0.5, times its height, 1. Now, because we are dealing with an area, it's good to put that we're dealing with units squared, but we'll do that right at the end when we sum all 4 areas. Now on to rectangle 2. Its height we can get from substituting in x equals 0.5, right, just here. 0.5 is the x value that when we sub it in, hits the curve at somewhere around here. So let's sub in x equals 0.5 into our function, and we get 0.5 plus 1, and that's all squared. So what is 1.5 squared? Well, it gives us 2.25. Okay, so a little bit harder to read that straight off the graph, but very easy to work out if we just use the equation of the parabola. Okay, so area. The base, 0.5, times the height of 2.25. That gives us an area of 1.125 square units. Rectangle 3. We already mentioned before how this rectangle has a height of 4, but let's just double check it algebraically. So it's at x equals 1 for this third rectangle, so we're going to substitute in 1, and we get 1 plus 1 all squared, which is equal to 4. 2 squared is 4. So our area for this rectangle is 0.5 times 4, which is just 2 square units. And our fourth and final rectangle, which will be the largest one, can be worked out as follows. Its height is what we get when we substitute in x equals 1.5. See, just here, this value. F of 1.5 is equal to 1.5 plus 1 all squared. 1.5 plus 1 is 2.5, and 2.5 all squared is 6.25. When we then go and multiply by 0.5 to get the area, that's where we'll come out with our 3, Mr. Laurie. So the area is 0.5 times 6.25, and that is 3.125. So we can take these 4 rectangles and come up with the total area. So the total area will equal the sum of the 4 rectangles. 0.5 plus 1.125 plus 2, and our fourth rectangle is 3.125. And so this gives us 6.75, and now we'll put in a units squared. Keep in mind, however, that we have underestimated. Right, so the true area is this blue area, and we can see little bits of blue still visible. So our true area will be more than 6.75. Let's have a look at part B now, where we're going to use outer rectangles. Now, once again, because we're using 4 rectangles, okay, we're going to have each rectangle having a width of 0.5. Okay, but starting from the right hand side this time, so x equals 2, we draw our first rectangle by going right up to the curve, okay, and then going across from there so that our rectangles lie above the curve. So our first rectangle on the right there that we've drawn is going to have an x value of 2, and then we'll use that to find its height. But let's draw in our 3 other rectangles. So going up at 1.5, hitting the curve, going across and then down. So we're halfway there. Our third rectangle, and our final rectangle. Okay, let's go through the same process as before. We'll speed it up a little bit this time, but just keep in mind that this first rectangle we're going to look at, its height is actually determined by this x value here at 0.5. Our second rectangle, its height will be determined by x equals 1. Our third rectangle, its height will be determined by 1.5. And our fourth and biggest rectangle is determined by x equals 2, giving its height. When we substitute in x equals 0.5 to find the height of our first rectangle, we notice that we've seen this before because we looked at this in part A, and so 1.5 squared gives us 2.25. Likewise for rectangle 2, when we substitute in x equals 1, we get 1 plus 1 all squared, which is 4. Now, just to clarify, this green rectangle, I probably should have gone up a little bit higher over here, yeah, because we've got a height of 4. Okay, rectangle 3. We are going to use x equals 1.5 for this one. When we substitute 1.5 in, we get 1.5 plus 1, which is 2.5, and then when we square that, just like previously, we get 6.25.